Okay, now, thank you to be here. Let me now open the presentation of today. Let me share so you can find a little bit also in the electronic, in the e-learning, how it looks like. You can find here how it looks like, the presentation which you have in the e-learning system. Introduction to model predictive control. As I told you, we will emphasize the application part. This means we will skip mathematical aspects because, as I told you, we have just this lecture and other 3 lectures. But it could be that once I will not be here, of course, we will recover somehow. Probably we will prolong the last one. But in any case, to tell you about MPC, to apply MPC, and then the idea is to tell you, even though very quickly, a little bit about the Kalman filter, it's really the time extremely short. Look at this picture. We can see just, I would like to say, if you consider here quickly, that the model predictive control can be seen, or you can figure out, that consists of, let me say, 2 parts. No, we can see in this scheme. We have the description of the process of the system. Detailed is written. Process understanding, basically the model. Understanding of the processes, in our case, in a model. We have seen also, the previous lectures. We started always from a model because, in the modern control system in cybernetics, nowadays the control strategies are model-based, and in particular model predictive control, because in order to predict based on a model, we need a detailed process understanding. If we don't have, our question is, what we can do? Can we, excuse me, is it nevertheless applicable, MPC? If the model is not detailed, of course, we have to find a way to adapt some parameters or some part which allows a little bit to find a compromise. If something changes in particular, this means a little bit the idea it is not detailed, that over time some parameter will change, excuse me. This means basically that we have to provide step by step, we will see what is the meaning step by step, to update the model, which allows to predict. And in order to overcome this lack, which is a lack of in terms of knowledge, of course. Therefore, detailed process is a little bit is defined or is expressed in a really wide meaning. Basically, we have to say we have to know everything, or in the best way which is possible, because the model is useful to predict, and to predict something in the future. I didn't specify, but it's clear what I intend. The prediction is related to an event or something which will be in the future. Must be the model with which we predict, let me say, as much as possible precise. And then the second part, and this is the optimization part, is an intelligent part, which basically nowadays characterizes the model control strategies. Exactly, optimal control, I would like to say, an optimization method. Combining a detailed model with an optimization method, this is the idea of the model predictive control. Okay, a few information. I don't want to invest much time on this historical or structural information. We will see a little bit more in depth the applications. Yeah, it's relative new as a method. We can see 1980. It seems to be many years, but in research, let me say less than 50 years. It's just not in a long period in any case. Very important that it works in discrete time framework. Um, I can eventually tell you something about the discrete time framework, even though, as I told you, much time I don't have. But it could be that some flesh or flesh out, no, on some important top elements of this field. It could be that I can tell you. Uh, the sentence number 3 is a little bit in the challenge. It's a little bit in a challenge because I mean, it's written something which is not wrong. Partially overcomes the need of a feedback architecture. We learned always that the feedback architecture is the best way to control the system. Yeah, because we have information about the goal and we have information about what we want to obtain. We have the feedback. No? But of course, the sensei is even when something is very strong, when something is extremely powerful, we have to think that we have to pay a price for that. And the price is the complication and control algorithms. And the complication means calculation load or the running time very high, very heavy. Partially means nevertheless the feedback is there. But of course, the structure allows me to say uh, that I would like to formulate the most important part is nevertheless force and feedback. But we have a strong, let me say, feed-forward action, which in many cases is not so difficult to be implemented. I don't know if you remember the feed-forward action in control. It's one of the easiest the primitive in the sense method, but if integrated with the feedback, even though easy, even though alone cannot work because of robustness, really can help a lot. The total control structure. First of all, we simplify the feedback architecture. And as I told you exactly now, the feed-forward architecture or structure typically is easier to be realized than the feedback one. Yeah, as I told you already, commented this point here, we have an integration between the model and the optimization. We can apply also, we can include also problem in multivariables, not only one goal could be fixed. And we have a very good also, let me say, reaction of disturbances. Of course, not so good as in in sliding motor control, but to remember, in sliding motor control, we had nevertheless drawbacks. Again, if you obtain something very important, very powerful in control, basically you have to pay more. Not only in control, no, not only in control. In general, in our life, not to obtain something with values, of course, we have to pay time, the money. It depends on the field. Yeah, here we have a nice picture in which we can see two important concepts: uh, past control moves and control horizon. In particular, control horizon. We will distinguish this control horizon in two horizons. Uh, we will see prediction horizon and control horizon. This means here is just partially represented, but very often they have the same length, control horizon and prediction horizon. And this means in some books they speak about just a control horizon. In any case, the control horizon is always less or equals the prediction horizon. It's clear because I can control just E, just if I can predict. This means the control horizon is less or equal, very often equals the prediction horizon. Therefore, this picture is you can find in many books. And of course, this horizon will move. Now we understand now practically with SimuliMATLAB, with the simulation, what I intend that will move. This means we have also an horizon, or why not, in a past horizon, if you want. Oh, here is written past control moves. In any case, what is in the past is already at disposition. This means we can use if we want to use. We can see here how possible to say from the picture that we are able to maintain the inputs. We can see here. Think about the signal here as an input, but also we can consider the output, both, considering some limits, both inputs and output. Here it seems to be that the picture is referred to the output, but if you look in some books, the same picture, a similar picture with stepwise continuous function are show for input or output or both. The idea is, or at least with this method, we can contain or we can maintain input and output inside limits. For the input is extremely important in terms of power because we cannot to have a signal as an input for any power because the system has a limit in terms of power. And also the output is important for a different reason for the precision. We want to an output between 1 minus 1,5 and plus 1,5. If the goal is ideally 1. Yeah. Basically, we can summarize everything which I told you until now in this form. We have a model. We have the past input and outputs. As I told you, these elements, if we need, are at this position. Using the model, I will predict outputs. Now we will see concretely with the example. And the optimizer, or better to say, the optimization method, is nevertheless inside the computer, the microcontroller, which takes the prediction output and the reference trajectory. Basically, here we have a minus, no reference trajectory minus the predicted output. And then, which is basically future values. Why that? Because how possible to say, through the model, I will predict the difference between the reference trajectory and predicted output generates future errors. Think about in terms of vectors. We have a vector of element of reference trajectory, which I know in advance, because the goal must be known in advance. We have predicted outputs, the difference in between generate and future errors. So predicted means future output. And this future error can be optimized. I mean, I will try to find future inputs, including the actual inputs, of course, which minimize the errors. Of course, the optimizer or the optimization method uses a cost function. Together with the cost function, also the constraint. Not always the constraints are present explicitly, but if you remember this picture here, we can also try to include the constraint explicitly in the algorithm. Very important that the optimization method or the optimize, I would like to say, sometimes optimizer, I copy this from a book, but I like to speak instead of optimizer, it will be It's not wrong, it's not wrong. I would like to say solver, which is associated to optimization method. Optimization method is wider than solver. There is a solver, but the method means to choose in a particular suitable cost function. And yeah, of course, this is more or less what we need, but also extremely important that how long is this future errors. This means depends also on different aspects, a little bit not so easy at the beginning to be understood as the sample time and so on. But anyway, flesh out, keep in mind this, I will come back in a few minutes for a final scheme that can help definitively more than this one. Yeah. Here, basically, I already a little bit told you what I am intending here. Very important, probably, I mean, this slide here is more or less something more what I told you until now about the characteristics of this model predictive control. Again, we can see here that we have the future in the past. That's not a big problem. Here I represented just the manipulative variable, the U. We can see clearly that we have a control horizon and a prediction horizon. Because we have the matrix which allows to build also this two concepts practically. I will tell you. Very interesting from this picture that the upper part, past the future, I already told you, the x-axis is characterized by discretization of it, K is in the count. We can see from the upper part that the MPC starting from 0, he will try to minimize the difference between time corresponding, of course, difference time corresponding between, let me say, the goal, these blue dots, reference trajectory also sampled, and our, let me say, prediction, this empty bullet, and to optimize, to minimize, for instance, the sum of the error square, something like that, we will discuss later about this, about how we can build this future information. And the hyper, let me say, let me explain a little bit better. And that the goal is to minimize the cost function related to the error. This means the difference between blue dot and the empty dot for the future, starting from k equals 0 from the present. But of course, each time we will update with this receding horizon what we have at disposition, then we will adapt our control strategies to minimize the cost function of the error until the goal. The goal is this set point target, this dashed target. We will come back on this at this moment, just this I already told you, this page, just to a little bit to start softly. Basically, some authors said continuously that the chess is as control, because the people seldom accept to lose. Let me show you this concept. MPC is the playing chess and playing move my head. I think here I already told you about this economical cost using this method, and to conclude, economical cost in the sense the complexity the sense that the running time. We can see also from the scheme here. And then very often we will see, I hope to be able to show you, we need an observer to adapt the model, for instance, but not all, the model of the control structure. Let me conclude with this picture. It probably is more oriented to our course in terms of states. In fact, we have a plant. We have a feedback. We can see how we measure at something. We have a noise. Nevertheless, we try to model in the best way we can the plane of this phenomenon. And we have basically two outputs, which is the predictions. At the end, the model will offer the possibility to predict the future of what? The states of a system which we are considering. States of the system. This is never wrong, no? Okay. I think also this part, I told you a little bit at the beginning, I mean, not explicit in this form, but the MPC replaced in a great part of a PID controller which are on is present or which are or in any case present to America. So let me show you now more in depth the linear model predictive control before starting other questions. What happens if the system is non-linear? Could we nevertheless do it? Of course we can do. Of course we have to consider some possible approximations. We have to go in depth in the approximations. But in any case, as is possible. I have a couple of references which I use in a course just dedicated, only dedicated to the MPC. Look at the scheme here. We have an electrical circuit. And I can write the equations. This in which we have an in the background, let me say the color red or something like that, in which the current with respect to the T is 1 divided the LU input minus R multiply the current minus KE dot apostrophe omega. This is an equation which we know. I did this example many times also in the previous lecture. No? We have an RL, let me say C circuit. And then we have the second equation, which is the equation, the mechanical equation of this system, which they are quite similar. I don't know if you see the similarity, a little bit, a little bit, not exactly, but a little bit. I told you about the model of the friction. No? This is a really tough topic. But anyway, let me consider just linear because I would like to introduce the linear model predictive control. The second equation we have seen is the mechanical equation, the dynamic equation of my phenomenon. Okay. Let me consider a reduction of the model. Why that? Because if you look at this matrix here, now in this case, I don't need reduction because I forgot that in the first version of the model, we don't have the derivative of the position equals the velocity. This means I can realize this equation 1 as equation 2 in this form, just considering that the Jewish in Germany are the same this year as 20 years ago. This means we have, of course, the necessity to improve our fields or to explore different fields. But of course, very often, at least in the didactical sense, we have tried to consider in the lecture just a topic and arguments which we know. The matrix representation of the previous system or the previous representation, this one. I think you can believe me. Just to translate, remember I told you, translate this information into a matrix 2 times 2, which multiply the states and the derivative of the states. Now, this is its representation in terms of a block diagram. We have seen in other contexts, but it's quite similar. Sometimes it's useful because we can recognize directly the interconnection, the physical interconnection between the variables. We can see here a little bit how the system works. Okay, now more in depth. I have in my case the equation 1 and equation 2. This is the equation, the linear equation of, let me say, of dynamics of the actuator. The current is one state, the second state is the velocity omega. Now, we will see they both appeared in Scopus. Look at the following position. IT, the current in continuous, equals I of k minus 1, everything multiplied t, or the ts. In this case, sometimes we write I of k minus 1. The reason is, inside the argument, the ts can be at least in this nomenclature not considered, because in any case, for a given ts, we will obtain definitively the states, the representation of the states of the system. The same consideration can be done for omega. We can see at the end of the page the derivative of the current, the dynamics, I would like to say, of the current, the dynamics, I would like to say, of the omega. Now, the question is at the beginning, how it looks like the model now? Because you remember, we have seen how it looks like the model in continuous. Now the question is how it looks like the model in discrete. We can see the equation 1a states how we can expect, or how it is, the equation from the dynamics of the current. The same consideration can be done for the dynamics of omega. Where this equation comes from is easy. We can plug in these two equations at the bottom in the equation, and also again ik, bak, everything which is in term of a, in term of t, can be changed in term of k. Now, we have both. We have both the dynamics of omega, the dynamic of the current, plugging in equation I1, we can obtain the dynamics of the current, except for the constant. To remember this, we did also in the gymnasium. Now, please pay attention here, and then we take a rest. Look at these equations. We have the model in matrix and vector form. I already told you about that. It's a way to represent the system directly using the matrix, even though sometimes it's not appropriate to use directly the matrix. When it's not appropriate? If you have errors and errors, which in which sense? The matrix typically is in a representation, in terms of matrix and vector. This holds just in linear system. This means if I linearize or if I don't consider the nonlinear part, of course, it's not suitable because you have an error. I mean, to give the priority to build the system or the modeling with the matrix, it's something which not always works. I would like to say it's as difficult you have to consider other elements around the control systems. Anyway, here's the system, which starts now from k equal 1 until v. Before, we had a little bit different. I don't know if you remember. Started from 1 until n. Until n here. here in this representation, we will start by 1. In fact, you can see at the end, we reconsider in a similar notation, but we start from 0. So this last configuration at the end is totally convenient, totally consequent with respect I don't have with respect to the other methods which I have presented, I told you until now in MPC. We are here. No? And then, of course, the same, no, it's not, we are a little bit, yeah. The same consideration can be done as before for H and G. And of course, at the end, I can write there's a final version of the model using the math AK, BK, and CK, which is defined exactly before, but starting from k equals 0. So we have a perfect compatible representation because once is starting from 0, once is starting from 1. Look at these calculations, even though the calculation we reconsider after, we can see here, after taking a cup of tea. What is the meaning of this nomenclature? Directly from here, if you want. Here is a linear system or linear time linear system in which we have the states of tomorrow as the function of the state of today plus the input of the state of today. The same here. But the problem which arises here is what is the first value of age if nobody works? Yeah, the task of way, the task of MPC is to predict this means from the data of today and the past data, we have to be able to predict somehow what happens in the future. To do that, we consider a prediction horizon. In this case, we will consider the prediction horizon equals controlled horizon. It's not always true. Typically, the controlled horizon is shorter than the continuous one. Okay, I think we can stop here. We will see in 20 minutes, more or less 15. So that's I can drink a coffee because I am sleeping. And we will reconsider this method, this method in one form in any case, and then we will implement. Anyway, the idea is to control something, the system, which could be linear, nonlinear, typically nonlinear, or a linear with time variant, with an algorithm, with another control strategy, which emphasizes the applications, considering some simplification in order to apply the MPC using the prediction to predict the future. I think I didn't forget anything. We will start from here in 15 minutes. See you in 15 minutes. I have a question before take a rest. About the Abgabe, I don't know when Niels will fix. About the Hausarbeit, we have to wait until the end of the course because, in my opinion, you should hear about the all topics MPC, and I hope that I'm sure to tell you something also more than MPC. And this means we can start on 24. But of course, could change if I receive the information that there is in a short time for the exam, for the project. This means we have to ask to Niels, but I think typically we have the months of July. This means we have a full month to do it. This is nice because the idea is to tell you everything and then you can choose. You can choose. I don't want to start now because in any case, we need MPC, but I think not only. I would like to tell you a little bit also uh, other methods. It could be that we don't need to recover this lecture, but in any case, let me go through MPC, then I will be informed about the when we have the deadline, and then we can organize. If you have the deadline in mind, you can tell me, no? So we can organize directly a bit our schedule. Let me stop a little bit here. The I think this is enough pause, no, because I don't know well. Now I read that the lecture is until 19 June. Okay, let me stop now the recording. Now we speak a little bit. Okay, 19 June. Okay, let me see. Let me discuss with you this 19. It could be. It could be. Yeah, but as I told you, probably 16. I am not there. This means if really the last lecture is 19, our last lecture is 9. If our last lecture is now, we have just 2 lectures. And the question is, the most important question is, ja, it's written, dann haben wir die Abgabe und Klausuren. Yeah, but when is the last day for the Abgabe? This is the most important question. Eine lecture mehr, eine lecture less. In this, it's important if you consider the percentual of the hour which we have. But anyway, in any case, MPC must be done. This means this we will do sure because also today we will give a good idea about MPC. We have to know when is the deadline for the Abgabe. And then we can think about to start earlier or to wait the end of the lecture. Let me drink something, otherwise I will sleep. We will keep in mind this problem, but if you are sure that the last lecture is 19, we have to start to speak about that, of course, because 16 on Wednesday, probably I'm not here. And I thought that we can hold the lecture on 24. We have another lecture on 24, but it seems to be shorter than I thought. Let me come back. Let me go away. I come back. Okay, I have seen you, ich habe Ihre Message gesehen. Praktisch scheint, dass ja, am 19. Juli, wir müssen alle Note erledigt. Macht ja Sinn, weil kann sein, dass ihr habt recht, dass der 19.06. ist die letzte Vorlesung. Das für uns bedeutet, weil danach hatten wir theoretisch einen Monat, ne, von Projekt und Benotung. Das bedeutet in unserem Fall, da sehr wahrscheinlich ich am 6. nicht da bin, die werde ich, weil am 19. ist die letzte Vorlesung, ja, ja, kann gut sein. Praktisch unsere offizielle letzte Vorlesung ist am 9. Das bedeutet, wir haben heute, dann wir haben die zweite, dann wir haben 9. Jetzt, meine Idee ist, dass ich noch zwei Vorlesungen, ich hoffe, zu Thema Kalman-Filter etwas erzählen kann. Heute, ich versuche zu fertig mit dem PC. Eventuell nächste Woche ganz am Anfang ganz kurz. Aber wahrscheinlich brauche ich nichts. Gucken mal, wie ich schaffe heute. Dann wir haben zwei Vorlesungen. Klar, zwei Vorlesungen ist extrem wenig für Kalman-Filter. Ich halte hier ein volle Kurz nur für Kalman-Filter. Aber anyway, sprechen die Stunde, die ich habe. Dann kann man so machen. Ich kann am 9. praktisch in 2 Wochen, sagen wir so, äh, schon die Aufgabe schriftlich zeigen. Und meine Idee, ein bisschen zu nachholen aus die Vorlesung, die ist am 6. Wir hätten aber sehr wahrscheinlich nicht haben. Wir können am 24. uns treffen, genau über das Projekt zu sprechen. Aber das macht auch ein bisschen Sinn, weil ich hatte eine 2 Wochen sogar, ein bisschen schon überlegen mal, ne? Weil am 9. in meinem Fall wäre meine letzte Vorlesung, falls ich am 6. nicht da bin, sehr wahrscheinlich. Dann als Nachholung am 24. Wir können hier treffen und dann, ich hoffe noch einmal ein bisschen die Software oder die Material, das schon in der E-Learning da. Und der Vorteil für euch, das erneute, ich gebe die Aufgabe. In 2 Wochen können wir ein bisschen spielen. Guck mal so, wir sind vorbereitet für mögliche Fragen am 24., wo meine Intention ist, keine echte Vorlesung, weil wir sind schon in Zeit, in der Prüfungszeit, aber ich sollte eine Vorlesung nachholen, wie gesagt, sollte, es wäre korrekt, ja? Und so, wir können trotzdem als Vorlesung, in Englisch wäre Office Hour, ne? Das macht auch voll Sinn. Es gehört zu den Vorlesungen, Sinne, ich erkläre ein bisschen die Antworten, die Frage. Und die Frage sollte es kommen, weil 2 Wochen ein bisschen zu gucken, äh, bestimmt jemand das schon runtergeladen, das Material, ein bisschen schon probiert, was ist, nicht klappt, was funktioniert nicht, was ist falsch, und der Sinn der Frage, mir zu zeigen, Zustand der Projekte. Ich denke, es ist eine gute Sache, so zu machen. Wir werden noch einmal nächste Woche sprechen, aber ich denke, können wir so die Situation sehr gut behandeln. Ne? Praktisch die letzte offizielle Vorlesung, falls Sie bestätigen, dass ich am 6. nicht da bin, am 9., praktisch heute, nächste Woche, übernächste Woche. Let me see, ja, sollte klappen. Ich habe, wie gesagt, der 9. eine Veranstaltung vor, diese war fast immer. Eventuell, wir fangen an wie immer 15 Minuten später. Das ist absolut. Nee, pass auf, heute ist Mittwoch. Ich mache falsch. Oh, ich mache total falsch. Ah, die Vorlesung ist ja Mittwoch, heute ist Mittwoch. Okay, das bedeutet, ich habe falsch gesehen. Das Problem, die ich jetzt hier habe, ich bin sehr wahrscheinlich nicht hier am 10. Mittwoch und wahrscheinlich nicht am 17. Das bedeutet, ich habe heute und nächste Woche. Hm. Auf kurz, am 24. bleibt mein Angebot, hier zu treffen, um das Projekt zu sprechen. Das bleibt, 24. sollte klappen, hoffe ich. Ja, sehe ich. Okay, das heißt, nur eine Vorlesung von Kalman Filter ist ein bisschen zu kurz. Wir können so machen. Gehen wir heute weiter mit dem PC. Nächste Woche, ich bin da, ist kein Problem. Am Mittwoch, der dritte, nicht der zweite, habe ich falsch in den Kalender geguckt. Wir geht weiter mit dem PC und ich formuliere die Probleme hier. Ohne Kalman-Filter. Der Kalman-Filter kann ich eventuell etwas erzählen, was außerhalb der Programm, der Projekte, der Examen am 24. Ne? Wo ich auch, wie versprochen, wir sprechen über das Projekt. Machen wir so, heute und nächste Woche, wir completen offiziell das Programm. Ne? Kalman-Filter übrigens wäre auch wirklich zu kurz dieses Jahr, dieses Semester. Ist nicht in dem Programm, aber werde ich vielleicht etwas erzählen, auch etwas grob, ein bisschen so, ja, macht mehr Sinn. Und dann wir sehen uns neunmal nächste Woche und am 24. um zu sprechen, eventuell etwas über Karma Fit, aber besonders über die Projekte. Projekte werde ich nächste Woche formulieren für euch. Ohne Kalmanfilter, nur mit dem PC. Am Ende der Vorlesung, klar. So, wir sprechen über MPC etwas ruhiger. Ich denke, es ist eine gute Lösung. Und wir sehen uns am 24. Weil wahrscheinlich, ich hatte gedacht, war Dienstag die Vorlesung, dummerweise. Aber Mittwoch schaffe ich nicht zu sein. Weil ich gehe weg sehr wahrscheinlich Dienstag abends, Nachmittag, deswegen war unsicher. Aber Mittwoch, beide Mittwoch. Okay, aber gehen wir weiter. Ist nicht so dramatisch. Jetzt ist wichtig, dass grundsätzlich das Programm ist da und zwar das Sliding Control ganz wichtig und MPC, weil ihr auf jeden Fall in Kybernetik, das ist mehr Kontrolle auch als Beobachtung, mehr Steuerung als ja, die Kontrolle ist wichtiger. Aber etwas wollte ich ein bisschen so außerhalb des Programms über Karma Fit erzählen. Kommen wir wieder zurück. Ich denke, läuft, ne? Hm. Let me share. We were, don't remember where we here. Here I told you. Hmm. Let me restart from here. No, plugging in. I don't remember where we were. I think here we were, but let me restart from here, no? Because it could be that yeah, I did too fast. Okay, yeah, here I did extremely fast, I think. Uh, the sample time. Now, if I consider the sample time TS, I can write that the current at time t equals the current at k minus 1 multiplied ts, that for sake of brevity, to simplify the notation, typically inside the argument we don't consider ts because nevertheless is there. No? Nevertheless is in a way to say that we get values considering the argument of the function sampled, the sampled argument of the function. This means Ts is never considered in the future. We can consider also the approximation of the derivative in this form here. This is probably know from Gymnasium, no? The derivative of the current equals ik minus 1 divided Ts. Basically, the value at time k of the current or the omega or the velocity minus the previous values, no? Divided the interval which I am considering between the two values. The time interval, to be precise. Now, this way to sample in this definition is the forward Euler method. This is written here in at the beginning of the slide. To be more precise, that is not a digitalization, we can say, is a discretization. But anyway, from the discretization follows a digitalization. But to be precise, in a discretization. Plugging in this position here into equation 1 and equation 2, we will obtain, after some calculations, the dynamics, the discrete dynamic for the current and the discrete dynamic for omega. We can see here in the red column. Again, as I told you before, we can express everything, equation 1a and equation 2a, in a matrix form. We can see here, it's in a matrix form. Probably you know, we can do that. I mean, row multiply column, row multiply column. This information which you have here, I already told you to think about that. No? This information which I have here is the same in the information 1a dot and 2a dot. Yeah, as I told you before, this representation here is in the form of k starting from 1 until n. Very often we use the representation starting from 0, and this we have here to translate +1. Let me see if I can improve saying something. Yeah, why this hat here? Why this hat here? Because the prediction. I mean, you can see already here, theoretically, we can also see from here the prediction. The current today, IK, is the function of the current yesterday, let me say omega yesterday, and the input yesterday, in form of forward Euler. We have a different form of discretization. Of course, this is just the forward, let me say so, Euler. But of course, we have also different methods. For instance, backward Euler. But I don't have time to tell you about these different methods. But anyway, this is the most used, the most important for, let me say, yeah, different reasons, I would like to say. But of course, also this method, even though it's the most used, presents some drawbacks, For instance, we will see that I would like to tell you exactly now. The system here, the representation of the system, even though starting from an asymptotically stable system, could, depending on TS, be unstable. I mean, its representation, this model here, even though the original model, the physical model is stable, depending on TS, can become unstable. When TS is too large. The mathematical representation of the system, the physical system, which intrinsically is stable, more asymptotically stable, can become unstable if TS is too large. Can be demonstrated. This can be demonstrated. Nevertheless, this is very useful. For instance, presents the explicit form. This means explicit form. This means we can always obtain the future as a function of the present. In particular, if the system is non-linear, it's extremely important. If it's linear, also other methods guarantees this, but in general, this could be used for any kind of system, this forward Euler. Very often is more dynamic. This also could help, even though older let me say, approaches could be useful for MPC, nevertheless. This depends. It depends. But I don't have the time to compare and so on and so on. This is our compact form of my prediction, if you want, for one-step prediction. We can see, for instance, for k equals 0, we have x hat 1. This means the step future, if 0 is the present, is a function of the state at the present and the input at the present. And then I can calculate my output using this equation here, considering, for instance, as output the omega using this equation here, or considering a different output, for instance, the current. If you consider the current as an output, we have here this math here C, which is 1, 0. Yeah, I repeat it again. The model, as I told you, we will see now that we will distinguish, not in this lecture, but in the general approach, we have the two predictions or two prediction horizons, and control prediction horizon and then predictive horizon. Okay, now it's a little bit more complicated here, but it's not so much, in order to show you the structure of the prediction at P, in which P is the predictive horizon. Again, here in this, today, I don't have much time in this course, I will consider the predictive horizon equals the controlled horizon. But of course, could be different, and we will see a little bit the idea when they are different. It's not so extremely important to consider different, at least at the beginning. Change a little bit the dimension of the matrices. About the matrix, I will tell you in a few minutes. But in any case, the control horizon must be shorter with respect to the predictive horizon, or equals. It's intuitive to understand, because I cannot control what I cannot predict. Anyway, about the first equation here, I already told you. I already told you because it's the prediction which came from these two basic equations. If I plug in here x hat k plus 1 with this expression here, a multiply xk plus b multiply your input, I will obtain this. Easy, no? If I plug in this x hat k plus 1 with this expression, I will obtain this, which we can see, I remarked, the matrix is C multiply A, or CK multiply AK, and CK multiply BK, which is important to obtain the prediction. I mean, the prediction of step 1 for the given output, for the desired output. Desired output means the output which I want to control. Of course, I can predict both. No? This is the prediction of both. But of course, typically, at least in this course, we will consider just an output to be controlled. No, otherwise, a little bit, we don't have time to analyze. What happens for the second step? Look, y hat prediction, hat means prediction. Calculated that for k plus 2, can be, let me say, expressed with this form. How we can do that? Extremely easy, because if I add an element here, plus 2, I will have this plus 2, and I will have here plus 1, I will have here plus 1, and I can plug in now again this expression here. I don't know if it's visible. This expression here, again, this where here, which is after adding plus 1, we have plus 2, here we have plus 1. And believe me, this is also to see that we obtain these three elements. This here, when I add plus 1, is exactly this. And these two elements are there. If I add in here plus 1, I plug in this right expression. I think it's easy to see. And believe me, you don't have to believe, it's easy to demonstrate that adding other elements or the unit until P, believe me now at the end, we can obtain this expression here. Let me see if I forgot to say something now. I don't think so. Huh? K is the present, no? I don't know if this is clear. K plus 1 is morning. K plus 2, tomorrow in the sense. K plus 2 is after tomorrow and so on. And after P days. Of course, I speak about days, but we can see microsecond, millisecond, everything. Now, look, if I consider y hat capitalized as the column vector characterized by the output, this means I vectorialize this with this first component of the vector y hat capitalized. This is the second component. This is the p component. I will have this vector here as in a column, exactly looking at here. No? Equals g multiply xk plus f1 multiply u input of k. What is g in this form? Is the function, excuse me, the matrix, which multiply by x give us the contribution of x of this expression here. Basically, I'm translating this expression here into, or expressions into the matrix form. What is G? We can see very easy from here. Ck multiply A, Ck multiply A square, until P, Ck multiply AK up to P. Exactly this. We will see in MATLAB a little bit the meaning of this. No? What is F1? Everything which remain when I exclude the contribution of x capitalized of k, and this F1 is the matrix related to the product with the vector, the column vector u input k, which is defined here. Defined. It's not defined, I mean, it's summarized here because these elements here are exactly all elements in these expressions related to u input k. K plus 1, k plus 2, until k plus p minus 1. Now we can see, no? Because here, k plus 2, we obtain k plus 1. Here, k plus 1, we obtain k. This means you can believe me that this is the last, let me say, u input which we can consider. Nevertheless, this is the column vector of the u which we can consider, but the interesting aspect to be remarked is that this vector, the column vector, is the vector of the future input plus the actual input or the present input, if you want. The idea is to calculate this u capitalized input of k, which consists also of the future inputs. The actual input is easy to understand. The future input nevertheless can be calculated, but of course I cannot use. First of all, because it's the future one. I mean, I can use, but I can use just the actual input because it's what I need today to obtain the goal. Of course, at each step of this receding horizon, I will clarify the meaning of receding horizon. It's an horizon which is moving. No? Better to say moving horizon. Moving horizon. Moving horizon is the correct expression. Moving horizon, I need to recalculate again everything. It could be that's also not necessary, but anyway, if something changes and disturbance arise, at this moment I didn't tell you about the disturbances. But anyway, the horizon should move, no? Because the time runs. In any case, I will clarify a little bit better with MATLAB probably. Now, the most important aspect, I don't want to say the most important, but one of the most important aspects in the optimization is always the definition of the cost function. Do you remember in the initial scheme I told you about a cost function? Here we can see how we can define this. No? There's a possible definition, this one, in which we have the particular expression of the cost function, probably, yeah, can be better understood than here. I will try to explain this expression here, and then we will come back on this expression here, which consists of two parts, if you think. Weighted part, Q, weighted by a matrix, Q and a matrix R. Of course, if the predictive horizon not equal the control horizons, yeah, we have some different length of the matrix Q and R. I will tell you now with an example in order to understand better. Look at this YR. What is the YR? It's the vector, is the vector of the errors. We can see the errors of step one, in which YR hat is our reference. You remember at the beginning I told you that we have a reference. Let me come back. It's a vector. Yeah, the reference is exactly this blue, represented by these blue points, which can be considered as a vector. Huh? This value here, this value here, this value here is our trajectory to be set, to be tracked. Huh? We can set in the vector. This means YR minus YK here. I forgot. Oh, no, it's correct. I see now the hat. Transpose, multiplying a matrix of the weight. Now we can consider in particular this matrix also. Multiply again the vector, realize the error squared. Why that? Because do you remember? Y was in a column. Huh? YR minus Y hat is the column of the errors between the reference signal, or the vector, and the predicted. Y hat is the predicted. If I do the transposition, I have a row. Let's consider now Q as an identity matrix at this point, as an identity matrix. The row multiplied in a column with the same value, we have the sum of the error square. This means this first part can be easy interpreted of the sum of the error square plus 1 divided 2. 1 divided 2 is there just formally. I will clarify why this 1 divided 2 is there. And here is the same concept. We have the input, which must be calculated. This is a no. This is a vector which is unknown. And at this moment, the length of the vector is exactly the length as in the predictive length. I don't know, we have seen here. No? I don't know where we have seen here. The length is P also here, no? Because it's starting from here to here. No? P is the length. P, excuse me. Yeah, more concretely, let me explain a little bit more concretely these elements in order to understand better. The example with an horizon of two samples, the easiest example. Now I called this YR hat minus Y hat E, the error. Y transpose because originally it's in a column, but I need here in a row because, yeah, I have to obtain at the end the sum of the error square. I obtain exactly the sum of the error square multiplied by 1 divided 2, but I will come back on 1 divided 2 later. No meaning. if Q is identity matrix. In the same way, if R is identity matrix, I have here the sum of the input square, which I have to calculate, starting from the actual value until P minus 1, the future. P is the length of the horizon. Predictive horizons equal the controlled horizons. Look at this in our case. Let me consider just weights, because this weight here is a little bit difficult to be interpreted, at least at this stage, at this today. Also this one, but this make more sense to be, at least we can understand well with respect to this one, because it's the weight of the error. Let me say, yeah, it's the error related of tomorrow. Here is the error related of after tomorrow. Of course, typically the error related of tomorrow must be more important than the error considered after tomorrow. Typically, the reason is tomorrow we will do again the calculation for after tomorrow, but it's important that tomorrow our goal is almost reached. Again, if Q equal 1, Q1 equal 1, Q2 equal 2, we have the 1 divided 2, A1 squared plus A2 squared. What about this element here? It's the same consideration. Of course, R1 and R2 are the weights considering the inputs tomorrow and the input after tomorrow. So in this case, it could be more important probably, you know, what we obtain tomorrow, because it's close in time, and what we are able to pay tomorrow. Yeah, probably I made mistakes because the first element is today. Yeah, we can see from here. Excuse me for the error, no? What I want to spend today to obtain something tomorrow. The error, this matrix, is starting from tomorrow. Clear, no? Because I apply something today to obtain something tomorrow. What is the something? To minimize the error. Meaning, the general meaning of this expression is I consider the cost function and a cost function which we combine what I want to obtain to minimize the error today, tomorrow, after tomorrow, and so on. And we have to consider what I have at disposition. This means I have to nevertheless minimize the energy in terms of inputs, in this sense, today, tomorrow, and after tomorrow. I mean, please pay attention on the timing. UK started from UK today, what I can apply today to obtain something tomorrow. K plus 1 is tomorrow. But of course, I defined in my cost functionality everything in terms of errors. Because the idea is to have a small error, ideally, a small error with small input. Of course, this cannot be reached. Anyway, we try to optimize, to obtain the goal with the minimal energy in input. But of course, if I put the error 0, the risk is that I will obtain an unstable situation. Here, the stability is not included in the analysis. Or at least is included indirectly. Because the idea is to limit the input U. Also in the practical stability, let me say so, even though practical stability very often is not a meaning, but practically, I would like to say, we have to limit the input U in order to have less energy losses, in order to have no oscillations, not to have effects close to the instability. But in order to obtain a limitation of the input, R must be relatively large. or let me say a little bit larger with respect to Q. We will see in the simulations. How we can now find the solution U, which consists of the input of today, input of tomorrow, and so on. I have here the demonstration, but I would like to skip the demonstration because it's quite boring, but I will sketch shortly. At the end of the calculations, we will obtain this solution here. The problem in this context here is convex. The optimization problem is convex in the sense. We have a convex function to be optimized, and then is a linear constraint. This is the constraint. Constraint means the conditions which I have in order and to minimize this. This is the solution which came if I do this boring calculation, if I do the derivative of J with respect to the derivative of U input, because believe me, we have to find the vector U input. Believe me, I try to clarify a little bit. During the calculation, which really is very boring because we have to consider this vectorial derivative, consider some property which we can see, one of them we can see here. Very important, nevertheless, to optimize that the problem is convex. This means that this condition, which typically is necessary condition. Do you remember in high school, the derivative with respect to a variable is just a necessary condition to find the minimum, the maximum, and doesn't matter what, also a settle point, but because generally we have to check also the second derivative, sometimes it's necessary the third derivative and so on. But it becomes a sufficient condition if we know that the function, for instance, in high school is convex. Or in this case, that's the problem. The optimization problem is convex. When an optimization problem is convex, okay, here's a little bit more complex to explain. But in any case, we need a convex function to be optimized. It's the case. It's the case because it's the sum of two convex functions. Error squared, even though weighted. Input squared, even though weighted. And then we have an input and constraint. As a constraint in which basically is clear, is visible, is separatable, very important, separatable what I know and what somehow I don't know in the sense. I can to express this. Probably we can look. Probably it is better to look the demonstration very shortly. If you plug in instead of y hat, this expression here I forgot hat because before we had yr hat, I think. Now let me see. Oh, no, we didn't have. But just starting from here at the beginning, I had, I think. Oh, no, I didn't have. I have here. Yeah, but this is not an error, no. Yeah, can be done, even though probably I will, to be precise, I will eliminate this hat. Anyway, I know the signals are known. If you plug in, where is? Yeah. Instead of y hat, everything, we can see that analytically, I can solve the problem. That means I can calculate U input because I can separate what I know with what I don't know. During the calculation can be understood probably very well, very bad, and something better. Using some properties, which I don't want to now to really to be heavy with this mathematical expression. This is in the property of the vectorial, let me say, derivative in the sense, but this isn't just in a formal one. This is another property that is useful through the calculation to obtain here the solution. If you want, you can look at the demonstration alone, but it's not necessary for the examination for the project, but a little bit to understand how we can obtain this equation here. But it's just a plugin and then to apply a couple properties to obtain basically the results, because basically this expression here is, if you remember, exactly the gradients, put to zero, using nevertheless this property. Okay, here we can find, here is again the solution. You can find here basically a couple of literature if you want to go in depth on this topic here. If you think about possible variations, sometimes we are considering U constant. Okay, why that? The reason of this hypothesis is different. Practically, often we don't have very long prediction horizon or the predictive horizons, and this means if in particular TS is very small, we can consider really just the first element. Nevertheless, just the first element is relative, is important. But if I consider constant, of course, I find a solution which is not exactly, the same as is the element and not constant. Because if the element U is constant, the matrix here, the vector here, better to say, consists of every element UQ is clear. That is an approximation in any case. No? What is the approximation, to be precise? It's here. Instead of UK plus 1, I put UK until this element here. This means what change? If every element of U is UK, we have F1, which I will call here F1 tilde, with just one column. If I have just one input, of course. I don't know if it's visible, this. Instead of this one, we will collapse into CBK, first row, second row CABK plus CKB, and then I go ahead until the end in which I will sum the contribution, because we have just one UK here, UK on second step, UK on third step, and so on. Now you can see that I will add. If I have just one input, I have just one column. Of course, the solution is different, because I assume it that at the beginning, the U does not change. Okay. This I would like to skip at this moment because it's a little bit advanced, something related to observability. Excuse me, controllability. Look at this. Delta UK equal UK minus UK minus 1. This means UK is delta UK plus U of K minus 1. Let me consider, what is the idea here? Let me consider the increment of U. UK minus 1, we know, no? Is the past U. Everything is the past I can store. I can redefine my cost function in terms of delta. Basically, it's just in a formal. It's just in a formal position. Yes, it is, But nevertheless, now with this formulation, also the past contributes to the solution because the past contribute to define the cost function. I don't know if can be understood this. This means now we'll try to find delta U. And then, of course, I know UK minus 1, I can calculate delta. I can calculate U, excuse me. Once I have, in this formulation here, calculated delta U capitalized, I have all delta U not capitalized. I can recalculate U not capitalized, just thinking that delta U K, let me say, equals UK minus UK minus 1. This means UK is delta UK plus UK minus 1. This is written here. But the advantage here, yeah, is that I am using the past, one past control inputs. Very often we can realize that this is a little bit more accurate results. Okay, here we have a C, no? This form here. And if you consider now the constraint or the prediction, the prediction the same way can be split. Do you remember here we had F11, which multiply U of K. But now U of K is delta U input plus U input K minus 1. Because in U input or delta U input, we have both contribution. No? Yeah. Let me see if I forgot to say something. I don't think so. No? Because here we have F11, which multiplied this UK originally, and then we will multiply FF1, this delta UK, and UK minus 1. Therefore, excuse me, therefore, this expression. The goal is always the same, no? To calculate the same. This case, to calculate the delta. No? And then when we have the delta, we have a U, because the reason is we have a U input K minus 1, we can calculate U input of K. Our goal is to have the actual input. Yeah, if we redo all calculations, your calculations, we can build the F11 matrix, which is basically not so far away with respect to which we have. Let me show you. We can see CK multiply BK, 0, 0, 0, CK multiply AK BK, CK BK. This was no, instead of F1, now we have F11. Eh? This is it. Exactly. At the end, we have this is a function of prediction horizon, which in our cases, I told you, equals the controlled horizons. Mm. Yeah, I told you anything, everything. I try to look if I forgot to say something. Mm. And yeah, again, um, why this F2? Because you have just one input, no? At k minus 1, no? uk minus 1. Therefore, one column. Now, well, let me check again this expression here. I hope no mistakes. Mm. I'm checking. Yeah, no? I'm thinking about the differences, but it seems to be correct. Because here we have the step P, no? This is step P. We appear here as P minus 1. And here we have also this element which I have to consider, no? Which we have A up to P minus P, I think, no? Because the step is P. But here M is P minus 1. At this position here. It's written basically here, no? If you think. Just theoretically, to think theoretically. That is, yeah. At the, at the step P, prediction output P, we have the input of P minus 1. Do you remember? I told you this. Everything is okay. Yes, a little bit, we have to be careful with the input conditions or indexes, but it's intuitive. Because, again, the concept is this here. Excuse me if I go up and down, but allows me to, you see here, no? Starting from K in the vector of the input until pi minus 1. Or better to say, K plus P minus 1. This means you have a P elements of UK, of U, let me say. But the same P elements we have here, the same P elements also in the prediction, errors in this case, or output. No? Exactly what you have here in these slides. Okay, we clarify. Please pay attention to my words at home just to understand better. In the simulation, we don't need to do this consideration because it's almost automatically, at least in the case when the control output equals the predictive output. About that, I can say use something more. And then we will conclude. We are almost at the end for this method. Look at this example in order to go in depth a little bit on this prediction and prediction and control output. Hmm. We can see here uh, exactly what I intend. We have the matrix Q, 2 times 2, and the matrix R, 2 times 2. The prediction horizon, we can see here, is 2. This means characterized by this row and this row. Is row oriented, let me say. If you look at here, we can understand. First element, second element, but row in the sense. If you have just two steps, we have two row for the prediction. Just to be familiar with this. And if the control horizon is also two, we have also two row. But it could happen if I have just one row. Because in any case, could be also less than the prediction, the predicted. What I cannot do, because we cannot find the solution, if we have two steps in control horizon and just one in predictive horizon. We cannot find the solution. We can see probably also easier from the calculated solutions because these two dimensions are not compatible. Here we have a matrix 2 times 2, and here we have a scalar, if I don't make mistakes. I'm not sure. Let me see. Where I made mistakes. No mistakes. No, this is possible because we have a, yeah, we have a scalar here, no? Because we have just this. Yeah, clear. Clear. I know the expert because I don't look for not conditions with no meaning. No? Of course, if the predictive horizon is longer than the controlled, everything is okay. But if I want to control something which I don't predict, of course, the mathematics or the expression or the structure of the frame, exactly here we can understand you have a 2 times 2 and here we have just a scale, for instance. And this is the dimension of the row. Excuse me if I come back, I go up and down. And the dimension of the columns represents, in any case, let me say we can see here, for instance, the length. For instance, here. Yeah, I mean, if the predictive horizon equal the control horizons, we have a square matrices. Otherwise, as I show you, uh, the matrix collapses no? Somehow. No? Let me see if I can improve a little bit better the For instance, if I am considering three predictive, you have to consider something meaningful, no? Three predict step prediction horizon and two steps um, control horizons. Look at the, we can see here a little bit better. Now we have A1, A2, A3, and this means we have a matrix 3 times 3. But here we have a matrix, let me say, two row and three columns. Let me see if I maybe six. I never use, or seldom use, I don't have in mind. Should be correct. Let me see. As I told you, for Q, nevertheless, we have an square matrices. Yeah. And here is not in the square matrices because we have a three row, but two column. Yeah. In our matrix because we have just two U. Because we are shorter in terms of U, let me say. Just two U if you have the control horizons with two dimensions, but three rows because this is determined by the prediction. Let me see if I made mistakes, but I don't think so. I seldom use, I don't remember exactly. But it made things probably. The contrary, excuse me. No, I told correctly. We have, let me see. I think three. I am not able to see exactly. Let me think. I will answer probably next week because I seldom I used. I don't remember here. I am not able to. Um, mhm. If I have two steps as control horizons, we have just these two elements. Okay, the matrix two times two. The matrix two times two for R and the matrix three times three for Q. Okay, I think so. But let me say I used center, I don't remember now. But in accordance with what I see now, quickly should be so. The last consideration, and then we take a rest, and then we try to simulate a little bit. This I already told you, and the horizon is a constant one. A constant elements can be useful for very short controlled horizons and or very short sample time in accordance with the slow dynamics, no? Slow U dynamics, which will reflect the dynamics of the system. Again, U vector is unknown. This means we have to wait for the results. But of course, the U reflects the dynamics of the output. This means if I have to predict the relatively slow dynamic system, of course, also U, it seems to be, we wait for slow variation. Of course, also this depends what we want to obtain. If the reference signal is fast, I mean, this hypothesis must be verified a posteriori, no? If this is guaranteed that practically means no many changes between UK minus one, but generally this happens for very short and very high very short, let me say, predict horizon, very short simple time. And in general, if the error between what I want to attain and what I have, this means our error signal is not so high dynamics, no many changes in it. If you think about this, I already told you, this delta can help to obtain better results because we are using an element and information more. No, this means more robust. This means yeah. In any case, we use something which before was not present. Of course, can help. As I commented, this is basically the formal solution in terms of delta. And that, of course, to obtain U of k, we have to do this operation here. No? Delta, the solution which I have from the methods, plus U of k minus 1 is this. Delta is the solution from the methods. I have to add U of k minus 1 to obtain U of k. The last consideration, really a few words about that. We will take a rest and then we conclude with a couple of simulations. And we will continue next week with the simulations. But today I would like to show you something. Look at this scheme here, or this description here, in which we include it also a disturbance with its map. D of k is the map of the input, which is an accessible input because it's a disturbance. It's like B, no? It's like B. I have in the simulation which we can understand very well what I intend. I do the same calculation as before, considering the prediction as step 1, step 2, step 3, and so on. Please pay attention. Here I know the map D, but I don't know dk. It's an input dk, but it's an accessible input. This means I don't know exactly dk. Probably I can estimate, but I don't know. D of k, we will see in the example, is in a map, is in a matrix, in a vector, could be also in a matrix, depending, which we know. Anyway, if I do the same calculation as before, considering now this hypothesis here, why this hypothesis? Yeah, first of all, to simplify and to find, and let me say, to find a reasonable solution in this sense. If the change over time, the solution is extremely difficult to be calculated. This is nevertheless something which can be applied. Why that? Because very often we have the system which is faster than the disturbance. Or through the controller, we guarantees this. So this isn't a constant. This means practically does not change much. The solution which we have in terms of delta, is quite similar to the solution which we have here. We can look at this solution here. We have just add a little bit the matrix as difference, of course. At least this F2, if I remember well, let me see. No, if 2 is the same, F1 is the same, just the matrix, just the matrix F3, which is new. F1 is defined before, I made mistakes. F3 is new. Of course, if the disturbance is not constant, we don't have the solution, at least not in this easy form. Because this depends, remember, I don't remember the demonstration, but I remember that it's extremely complicated if D is not a constant. Here we have also the reference, but I don't remember now the idea. And F3 is something similar, quite similar to our, remember this structure here. Instead of B, I have a D. Because also here we have an input, even though this input is accessible because the output, the controller, but constant. I don't remember, I have to reread this paper here to understand again why the need of this hypothesis. In any case, this is a simplification which allows to calculate or to have a solution in easier. But it could be that if it's not constant, I am not able to calculate, at least in this easy form. But I would like to read again this. I would like to read again this paper. In fact, it's here because yeah, typically we applied without thinking about what we have obtained really. Okay, I will repeat a little bit this thing using the simulation between today and let me say next week, half lecture of next week, we will complete MPC, considering new simulation, coming back to the lecture, to the slides, let me say. And then the second part of next week, we will speak about the projects. This is the good program. And then we will see again on 24 to discuss if you need, but I think it's nice if we meet to discuss questions, problems, is something that doesn't work, and so on. Let me stop now 20 minutes, and then half hour we do one simulation to go in depth again. I have 3 simulations to show you. I think I have 3 simulations. One we will see today, which is we go in depth on this concept again, because the first time probably that you heard about that dimension also for me sometimes is not so easy, particularly if we are speaking about techniques or conditions, which I don't use typically. I use always the predictive, the length of the predictive equal the length of the controller, but it's not necessarily the unique possible solutions, but the most used. Yeah, 20 minutes and we come back. Let me now stop here if I able to do. Okay. See you in 20 minutes. What we have seen until now, 3 possible schemes or strategies, better to say. One, just considering you capitalize with let me open again the lecture so we can classify better what I intend. Let me share. So it is clear what I would like to simulate today. Why I'm speaking about 3 possible structures. One is this one, as a solution. You input, no? As in a vector which considered the actual, you remember, exactly what I told you at the beginning, the actual input and the future input until p minus 1, which we are considering again the vector of, let me say, u, in which u is u input of time k, u input of k plus 1, and so on. Basically, the structure of the problem, of the predictions, is this one. And then we will see today together, and then we will stop for today. Yeah, again, we can see also in this form here, everything in compact form, in which the solutions, or the solution, I mean, we have solutions if you think more states, or the solution if you think in general the structure of the solution, or one output in, if you could say one output. It's characterized by matrix G and matrix F1. Of course, the solution consists of this form here. I will show you exactly now. Which came from this condition here, which is, in our case, necessary, but also sufficient because the problem is convex. Next week, we will conclude everything, considering the second structure which I told you. Or, yeah, we can consider also this here, which is a variation. So very often that is considered a variation of the first scheme. If F1 equal this, it's easy it could be that I have a time to do also today. We have a solution a little bit not so precise as the general solution, because we assume that U is constant. It could be that we cannot see the differences because the length of the horizon is not so long in the sense. We don't have many steps for the prediction. We will see. Then next week, in any case, we will consider this variation here, which, do you remember, I am considering now one element of the input, but the past input, U of k minus 1. And the solution, do you remember this here, in which G is the same, F1 is the same, F2 is this. F11 equals F1. Huh? The third one, I told you we have a three scheme. Here is the second one again with delta, which is a little bit more precise than the first scheme because we consider an element more, no? This one. The third one came from this proper formulation, which we have a disturbance, but constant at this moment. Again, the constant of the constants of the input, the inaccessible input disturbance, we call disturbance, can be justified or can be considered valid if the disturbance is relatively slow with respect to the dynamics of the system, if the prediction inside the prediction horizon in some sense. No? This means short prediction horizon and so on. This is the solution, which is based on this delta U, which we have to add this F3, but F3 is quite similar with the solution, if you consider the same, if you consider the solution when U is constant, but instead of B, we have D. Yeah. This matrix here, which basically is in a column, if the disturbance is just one element, one D of K not capitalized, no? D of K not capitalized. D of K must be known. Very often, as I told you, it is not accessible. This means we have to observe, we have to estimate D of K. I don't have time, it's a shame this semester, to tell you about the Kalman filter. Kalman filter allows me to say that D of K can be somehow estimated and then to be included here, to have a very good performance. But even though it's not estimated, we can nevertheless use this scheme here, or the first one, without the past value, to compensate not exactly, or not so well as this one, because if I know the disturbance perfectly, it is impossible to know the disturbance, because it's an external signal, because can be estimated, but estimated means estimated. I mean, we cannot know exactly what it is. Nevertheless, this scheme here, or this procedure, allows to realize a good compensation. Of course, with the assumption this is constant. Constant in engineering field means that change over the horizon, not much. What is the meaning of not much? It's clearly, it must be clarified. But we can compare with the dynamics of the system in this sense. If the signals in the system change, let me say, with the rate 2 times, no, is already to be considered the almost constant. But almost it's not exactly constant. Okay, I found now the software to be analyze a little bit. The first one, let me open MATLAB. The most important, the first one, the rest represent let me say, some variation. Anyway, if you think about this delta U, it's just in a position, but at the end we have in the solution the past value. And D basically is the prediction of D, assuming that I know, and D constant, or for a possible approximation, almost constant, or to be considered constant. I'm opening MATLAB now, and then we will see together an example. Mm, right. MATLAB is open. Let me see. Okay, here. I will upload later. Okay. Yeah, I think. Okay, let me open here the data. Hmm. Here we can see the data of a real motor. Data of a CC motor is a very small motor, which we can see the resistance 11 ohm. Km is basically this the constant we characterizes the motor. Inductance we can see here. J is the inertia. Kr is the friction, which we can consider the friction of the axis of the motor, or in general, the losses, the mechanical losses. TS is a strange number because probably some student asked me, I don't know why this, anyway, we can also test with different values. Simple time, TS, do you remember I told you about the simple time? The simple time, nevertheless, is extremely important because, how possible to say, uh, if you look, I don't know if I have here. Yeah, probably yes. Yes, let me go ahead and I will clarify. I will try to tell you about the TS. Probably this is better. It's better if I tell you directly with the, let me say, slides. The reason is why TS is extremely important. Look at this, at the discrete model. Look at the discrete model. If TS is very small, this AK tends or the collapses to an identity matrix. if I collapses in an identity matrix, here I collapses in 0, we have this ik plus 1 equals ik. This means in the representation, I destroy the model. This means DS should not be small, should be large enough, but of course not so large, because I don't know if you remember a little bit, with large TS, nevertheless, we lose information about it, the signal or the sense of the system. This means there isn't TS optimal between very small and very large, or large in general. And you can try to do at home this test, T small, T is large. Also could be an impossible question in the project. Anyway, matrix A continuous, matrix B continuous, C 2 times 2, matrix D, even though we know that is 0, the matrix of the connection between input and output in the output equation. And then we will consider again C, but at this time, a discretization of C. Oh, no, I think so. Here is not the discrete. This is continuous C, even though we will not use this. Okay, it depends. It depends. Probably in Simulink, I will use this and this. We will. Okay, now see. I will use this C for the discretization. D equals 0 is related to this C. We clarify a little bit better with Simulink. The use of the matrix A, B, C, D, but probably you already learned from control. Look at the discretization. Instead of calculating as I did in the presentation, instead of doing in this form, I use the command of MATLAB C to discrete mode, continuous to discrete mode, in which I am using here the exact transformation. Exact transformation is not a form of transformation. It's not the Forward-Euler transformation. It's based on a different principle. Probably you heard about the transformation which connect the zeta transform with the S transform. Is related to this concept here. But anyway, it's not a transformation, which I didn't tell you because I didn't have time to tell you about it. Anyway, starting from a continuous AR, a continuous BR, a continuous C with just one output, a continuous D, which I consider just one output and one input, because BR consists of just one input in this structure here, because we have the voltage as an input. TS is what I redefined before. Here it seems to be that I used also DD as disturbance map, but I think exactly here we have the matrix F3, which I introduced at the end of the example number 3, but here we didn't use this F3. We will see that we use just F2. I think we used, in this case, just F1, FG, because it's the first example. This means from here, we will see at the end, we didn't use anything. But if you remember the first example, let me say the easiest example, we have a solution in a function on F1, which is related to, let me say the map, the map of the input, which must be calculated, and F3. Just copy from the slides, believe me. How many steps, excuse me here. Yeah, just copy from the slide. How many steps we have? 4 steps. We can see 1, 2, 3, and 4. Just to check, just to test. I put R, and R I call here RW because R was also the resistance. And Q, it doesn't matter what. Just the diagonal element. You remember, I clarify why the diagonal element can be better interpreted. the mix element is difficult to be interpreted, but sometimes I have seen that somebody used, but I'm not so expert to understand or to explain why they do. In the cost function, you remember I clarified a little bit with the example 2 times 2 using the, let me say, the diagonal matrix. Let me run. Hmm? Now I have the elements. Let me open the files, Simulink file. Let me explain a little bit something more here, probably. Yeah. Global is in a function clear all we know, no? Clear all elements in a prophylax command just to cancel what we have in the workspace. Lower that trajectory, the data trajectory is in a M file, MAT file, excuse me, which is here. I don't know if you see here under the current folder, in which I stored the trajectory to be tracked with points. I hope that the file will appear. Ah, okay. Let me share now Simulink. Look, here is the motor, CC motor. If you go inside, we have exactly this representation using the matrix A, B, C, D, which I sketched before. The output is current and velocity is in the motor. If you go here inside, let me share also what we have here. We have the continuous matrix AR, which came directly from the model. We have the continuous matrix here, BR. Here, we have basically the disturbance, but I don't use it. The disturbance with the map 0, 1. I don't know if it's correct because I think should be 0, 1 divided J, but in any case, I don't use here. I don't use here this. I think so. Here should be the map 0 because the disturbance is in a torque, which is appear in the second equation, but appear divided by J. Let me come back on the lecture in order to understand better. I hope somewhere there is a continuous system. Yeah. I didn't put the matrix, but it's intuitive. I mean, if I consider here disturbance D, plus or the minus D does not matter, here inside the parentheses, it's divided by J. Here, the balance that you have here is a torque balance. It's divided by J. This means here is not exactly correct. I have to divide by J, but I think no problem because we didn't test here with the disturbance. The matrix D consists of 2 row and 2 column because the matrix D are the same row of C and the same column of B. We consider initial conditions in order to check the controller. Here, basically, if you look at the M file, MIT file, which is in a data file, probably you know, we can see that I save inside a vector of the time as a vector of the velocity. I would like to control the system in terms of velocity. This element here is also in the solution. We will see together. This could be at this moment disconnected. Nevertheless, I put it here. I put it because also with the scheme here, we can correct the disturbance, even though not perfectly or not very good, as I explain with the third scheme. We will come back next week, nevertheless. At this moment, without this. The model predictive control needs the prediction, need the states, current and velocity, in order to predict, using this software here, which I will present now, the output UK. The output UK. You can see here we have the UK minus 1, but we don't use it. We can see we don't, because this is the first variation. The UK, the input UK calculated by the MPC, is basically the input of our system. And if you think about it, this element here, x3 underscore s in output, is going input here, x3 underscore s, which is the input. Let me throw away the disturbance. What about the MPC? The MPC is basically implemented in this file here. I am using this interpreted function typically in order to be more, it's more easy to use this embedded function in MATLAB, but I didn't have the possibility to convert time to convert this is an old lectures in an old example. This is the file. Okay, let me open this file so we can, it's extremely easy to show. We can show how easy is the solution. The file, the name was this. No? Again, I declare all possible variables which I need inside the function. Here I redefine Q. It's not necessary because I put it also here, but sometimes to change directly. Anyway, this is redundant because I have here, but it's easier to put here. No? Also R. Here, we tested with R equals 0, with the risk that we have instability. Then we have a vector, an element T0, which is the time. It's a little bit, we can improve also the realization of the software, but in any case, is the clock, let me say. XA consists of two states, current and velocity. This is not used, this UK minus 1. We will see next week how we can use this in another variation. You can see now the meaning of T0. No? In order to realize an integer clock, I round T0, which is a clock which is realized by the ramp. Simulink is a ramp T0, divided Ts plus 1, but I round this. No? I round the integer value, starting from 1 to 3 and so on. Look, this is exactly what I told you before. This came, this vector here. Here I tested with two elements a prediction horizon. No, four, excuse me, it's in 4. Excuse me, I didn't see. It's in 4, as I told you at the beginning. We don't need anything here because I pass the element as global. So everything is, this is the solution. I mean, if one is inside the function thanks to the global variable SG. No? And then I will consider not the whole U, because I have to apply the actual, the first one. To remember, we have the actual value and then all of the future value. We will come back next week. Let me nevertheless show you simulations without disturbance. and then with disturbance. Because even though the disturbance is not included in the prediction, because this is another variation which I presented at the end, the scheme can help. Let me see without disturbance. Here's the results, or the results in terms of velocity. No? Hmm. Let me show how strong is this controller. Look at the beginning. Do you remember I put in condition 0 current and velocity 100, something like that. When you can see after some steps, the results is quite good. No? The controller works. Let me now include a disturbance. Even though, please pay attention what I am doing. No? Even though the disturbance is not included in the prediction. It's not the variation uh, with the, let me consider it something small, with the disturbance. Let me see if it's working. It's not bad. Of course, but why it is not bad? Let me show you the results. Yeah, more or less, no? As before. Yeah, we can see a little bit more oscillating because nevertheless is in a feedback structure there. But of course, we will see next week. If I consider the variation with the, let me say, knowledge about D and the structure in which D is in the prediction, we don't need a big effort. I mean, let me show you the difference. Do you remember I put Q very high in order to reject, to obtain the results independent of U. Do you remember R was 0? Let me show you. What is the meaning of this sentence here? Extremely high Q, extremely less 0 R. Means I would like to obtain my error as small as possible, independent of the price, independent of U. Because the cost function basically consists just of the error square or the sum of the error square. Consider on 4 steps. In fact, we pay this effect in terms of U. If you look at U, it's very high. Of course, to reduce, or at least higher, with respect to the variation in which D is included. The variation in which D is included, we have also, this is the U, no? Could be too much. We have also the variation of delta U, which is relatively better. But it could be that this variable is not acceptable for us. Nevertheless, it works. Nevertheless, it works because the system consists of a feedback. We have the error. The feed-forward action is basically this optimization method. Look what happens if I don't have the disturbance. Now, I disconnected the disturbance. Keep in mind this input. Without the disturbance, does not change much, just a little bit less oscillation because I didn't reduce Q. But now I can reduce Q because we don't have the disturbance. I mean, let me restart with the disturbance. Let me connect the disturbance again. Right. Let me reduce Q. If I reduce Q, in the presence of the disturbance, we will see that U will be less than this one, but of course, we will obtain an error in the input, in the output. Look. No so many oscillations. Of course, the amplitude is not so, but anyway, less than before. But what will happen in the output? Let me show. That the output is not so precise. Let me see. We can see. In order to obtain more precise output, we have to increase Q and this increase U. But with the variation in which D is included, we improve both, reduced U and more precision in terms of output. The reason is we have a cost function which consists of weighting, or the weighted, better to say, cost function, error square, the sum of the error square over the horizon, plus input square, weighted, both, error squared weighted over the horizon, and input squared weighted over the horizon. This balance allows to find a compromise, and the compromise is always an optimal solution, at least in control problems, but I would like to say not only in control problems, the compromise. We will see next week, we will conclude with MPC, and then we will speak about, I assign next week the projects. And then we have 2 weeks, probably a little bit rest, and then we will meet if you want, to discuss problems, to discuss something which doesn't work. Okay. Let me upload the material. So one simulation. Let me close here. I'm here for questions. I remain here to upload the simulation.